So at this point in the course, you guys have learned all the rules for derivatives. And if you recall from the very beginning, we said that the derivative of some function f of x, so the derivative f prime of x, was defined as the limit as x approaches some h value of f of x plus h minus f of x all over h. And now, in your heads, you guys probably think the reason we stopped using this formula every time to calculate a limit was because it was tedious and tiresome. And while that is true, the other reason is because we ended up in what's called an indeterminate form. Meaning, if we look at all of our indeterminate forms, okay, there's a whole bunch of indeterminate forms. The most common ones you end up with this class are like 0 over 0 or infinity over infinity, right? You calculate your limits, you can't really do anything. Or even like infinity times 0 means nothing. Or infinity minus infinity wouldn't really get you anywhere, okay? Or 1 to the infinity. There's actually only 2 left, so I might as well tell them to you. The other one is infinity to the 0 power and 0 to 0 power. So all of these indeterminate forms are indeterminate, meaning they make no sense. So whenever this happens, we have a very handy rule to use called L'Hopital's rule. So L'Hopital's rule, and it's spelled. So L'Hopital's rule and L'Hopital is the name of a person. It's not La Hospital, I promise you. So L'Hopital's rule says this. If you are given some function, so some function f of x, and it's equal to the quotient of another 2 functions, so g of x over h of x, okay? And if the limit as x approaches some constant c of g of x is equal to the limit as x approaches that same constant c of h of x, and both of those things equal 0, okay? Then we could say that the limit as x approaches that same constant of f of x is equal to the limit as x approaches that same constant, x of c, of the quotient of the derivatives of those 2 functions, okay? Oh, sorry, I put an f there. That should be an h. H prime of x. And now it looks like, of course, there's a double prime. We only want 1 prime. Okay, there we go. Now, L'Hopital discovered this to be true. Okay? I think about 15 years later, someone else who doesn't get any credit discovered that we could do the same exact rule if x is always approaching infinity and the limits of each of your, and the 2 functions also with the limit also approach infinity. Okay? So you can do it with any constant approaching 0 or x approaching infinity if both of your functions, when you take the limit as x approaches infinity, also equal infinity. Okay? So this is L'Hopital's rule, and it's actually not tested on your AP exam, but if you pass the AP exam, which you all will, when you get to next semester of calculus in college, they expect you to know this, and it's kind of a handy trick because you can actually use it on the AP exam if you ever get stuck. So let's go ahead and do an example. Okay, so let me move this up. So we're just going to do one example. Actually, maybe we'll do 2. Let's see how this one goes. So the first example, example 1, is we want to find the limit as x approaches 1 of x squared plus 2x minus 3 all over the natural log of x. Okay, sorry, this is a plus sign. So here's the deal. Your first step when you're doing a limit should always be to take whatever you're approaching and plug it in and see what happens, okay? That should be always, always, always your first step. So if I plug this in, if I plug in 1, I'm going to get 1 squared plus 2 times 1 minus 3 all over the natural log of 1, which is going to get me to 1 plus 2, which is 3, minus 3. So my numerator is going to be 0, okay? And the natural log of 1 would be e to some power, right? If you think about your exponent rules, this is the same thing as saying e to what power equals 1, and you should know that any constant raised to a power of 0 gives you to 1, gives you the exponent of 1. So again, this is 0, we end up with 0 over 0, which is indeterminate form. So because we end up in this situation right here with 0 over 0, we can apply L'Hopital's rule. So if we look back at L'Hopital's rule, it says that if we have a function that's the quotient, that's defined as the quotient of two other functions. So in this case, g of x would equal x squared plus 2x minus 3, and h of x would equal the natural log of x, okay? And if the limit as x approaches some constant, so in this case x is approaching 1, of your numerator, okay, your g of x function is 0, and that limit as x approaches the same constant of your denominator is also 0, then the limit of their derivatives exists, okay? Or you can take the derivative of the numerator and denominator to determine your original limit, okay? So let's do that now. So just to write this out really clearly, in this situation, g of x is equal to x squared plus 2x minus 3, okay? So g prime of x would then equal 2x plus 2, and h of x in this problem equals the natural log of x. So h prime of x would equal 1 over x. Okay, so now I can use my two derivatives, use those to write my fraction, and then take the limit as x approaches 1. Okay, so the limit as x approaches 1 of 2x plus 2 all over 1 over x. Now again, whenever you're taking a limit, the first thing you should do is plug in the value of your limit and see if it works. Okay, so I got to plug in 1 and see if it works. So if it does, I'm done. So 2 times 1 plus 2 over 1 divided by 1. So that's going to give me 4 over 1, which works, right, because we can divide by 1, and 4 is our answer. So even though our original function, if we just plugged it in and we ended up in this indeterminate form of 0 over 0, L'Hopital's rule allows us to actually calculate the limit, which is 4. Okay, so it's a pretty fancy rule that we have, and it's pretty simple if you think about it, right? Indeterminate form, derivative over derivative, plug it in, you get your answer. Okay, that's all L'Hopital's rule says. So again, it shouldn't be that hard because you already know how to take a derivative and you already know how to take the limit. But it's a little trick when you have an indeterminate form. So 0 over 0 or infinity over infinity.